Hello guys, how are you doing?
Hello.
Hi. So long weekends are coming. Have any plans for that?
Yes, have some rest.
Yeah, sure. Need to enjoy still warm weather in Kazakhstan. Mhm. Yeah, need to work also, not only relax. Hello everyone. Yeah. Okay, so uh, nice to see you guys. Do you have any questions? Uh, Something to discuss? I guess, as I understand, everything works fine with long kappa, no issues there. Okay, that's the most important. So, sorry. Today we continue our discussion of motion in two-dimensional space. And as a short recall of our previous discussion, we introduced the main parameters which describe motion in two-dimensional space, and also considered an example of projectile motion when we have a specific case of two-dimensional motion when there is constant acceleration aligned only along axis y, and there is no acceleration along axis x. So based on that, we derive equations which describe this motion and determine some main parameters such as maximum height of the trajectory and the so-called horizontal range, which is the distance from like initial to the final point of the trajectory along axis x. So today we will continue our discussion of two-dimensional motion, and our focus will be on such important example of two-dimensional motion as circular motion. So we will start from uniform circular motion when we have constant linear velocity, means by magnitude velocity doesn't change. However, even so, when let's consider some particle moving on circular trajectory without even changing the magnitude of velocity, this particle has some acceleration, which is called centripetal acceleration, and pointed towards the center of the center of the curvature along the radius position vector of this particle. And that is the origin of this centripetal acceleration is actually change of the position of the velocity vector. So it doesn't change in magnitude, however, it does change in orientation as the particle is moving along some curved trajectory. So that change in orientation causes this centripetal acceleration. And we will discuss in details where does it come from and how we can quantitatively describe this acceleration. So there will be like two approaches. First, more like physical based approach. We will consider literally the vectors and play with a little bit of geometry. And a bit later, we will analytically solve some equations, apply some rule of taking derivative, second derivative of a certain equation which describes position vector as a function of time for a particle which moves on a circle. And we will quantitatively, like analytically, derive this equation for centripetal acceleration, which is the only acceleration which body experience when moving around like along circular trajectory with constant speed, so without changing the magnitude of velocity vector. Okay, let me switch to the slide, and let us consider some circular motion. So this will be our circular trajectory. This will be the center of this curve. So let's consider 2 points, point A and point B. Point A is defined by initial position vector Ri. At every point at this trajectory, the velocity vector, let's call it Vi, initial velocity vector, is perpendicular to the position vector, because this is a circular trajectory. So in some time interval, which is defined as T final minus T initial, this particle is moving from point A to point B, and its position is defined by a new position vector. Let's call it R final. And it has this velocity vector, V final. So during this time interval, let's call it delta T, the displacement of the particle, actually a vector which connects points A and B, will be defined as this, and let's call it delta R, like change in the position vector. So now our important condition which we need to highlight, we consider uniform circular motion at this point, and that's why absolute value of velocity vector is constant. Means that the amplitudes of initial velocity vector is equal to the amplitude of the final velocity vector. However, as you may see here, the orientation of initial and final velocity vectors will be different. Okay, so now what we want to do next, let us take this velocity vectors vi and vf, and put them in the same point, like origins of these vectors in the same point, and draw it like below this first figure. So this will be our vector vi, and this will be our vector vf. So they are equal by magnitude, but have certain like different orientation. Taking into account that this angle, as I mentioned before, is always 90 degrees between position vector and linear velocity vector. If we have certain angle theta between our position vectors, then we will have the same angle theta here between the orientation of our initial and final velocity vectors. So the final velocity vector v final can be expressed as the sum of two vectors. It will be v initial velocity vector plus some delta v vector, which is change of the velocity. So we can show it here. So this is delta v vector. So now let us take a look at these figures, and let's say what we see. Since the angle theta is equal, these triangulars are similar. Means the ratio between two sides of one triangular will be equal to the ratio of two sides of other triangular. So taking this into account, we can write some ratio which is necessary for our further analysis. So let us consider first this lower, like velocity triangular, and we can write the delta v. So here I don't put vectors because we deal with absolute values, like when we take into this ratio between two sides of the triangular, we just take the lengths of these vectors, so they're absolute values. So delta v over v, so we can substitute this v initial, v final as just v, because the amplitude of linear velocity vector doesn't change over time. And this will be equal to, based on this similarity of two triangulars, velocity and position vector triangulars will be equal to delta r over r. So here we also need to highlight one thing. So as you see here that we have different position vectors, Ri and Rf, like initial and final. However, since this is the case of circular motion, radius doesn't change. That's why we can write that absolute value of Ri is equal to Rf, and this is equal to R, which is the radius of the circle. So from here, we can solve this ratio with respect to delta V and substitute its expression to the definition of average acceleration. So first, let us define delta V. Delta V will be equal to V times, let's say, divide by R and times delta R. So we also know from previous discussions that average acceleration, absolute value, will be equal to delta V over delta T. So now we know how delta V can be expressed. Here is the expression. So we substitute this expression in this equation for our average acceleration. And since our motion is uniform circular motion, average acceleration means also instantaneous acceleration, because the conditions of motion doesn't change with time, it's just constant. So we can just write A is equal to V divided by R times delta R over delta T. So let us keep this in mind. So maybe we can write it on the second slide. We can see it. Acceleration is equal to V divided by R times delta R over delta T. So now let us assume that these points A and B come close to each other. So we push these points closer to each other when they start to approach each other. In this case, delta T, like time interval, will also approach to 0, because if we have some very small change in position, means this change should happen within very short time interval. In this case, the delta R displacement vector, its amplitude value, will approach the length of the path between point A and B. So you see, path is this guy, and radius and this displacement is this vector. So if we have points A and B further apart from each other, obviously that displacement is smaller, absolute value of displacement is smaller than the path. However, if we push A and B close together, this absolute value of displacement approaches the length of the path. And taking into account all these factors, we can write that delta R over delta T, assuming that delta R approaches to the path length, delta T approaches to 0, is nothing else as linear velocity of this particle moving on circular trajectory. So if we now substitute instead of delta R over delta T linear velocity for this acceleration, which we can call now centripetal acceleration, we will get an expression. It will be V squared divided by R. So this is the equation for the absolute value of centripetal acceleration. What is important here that, first of all, as you have seen from the previous figure, for instance, this velocity triangular, this acceleration is not originated from the change of the absolute value. Vectors v initial and v final have the same magnitude. However, because of change of the orientation, we have some delta v vector, and that is the origin of this centripetal acceleration. Also, if we push these points A and B very close to each other, then the angle between this angle theta between position vectors and between initial and final velocity vectors will be approaching to zero. If this is approaching to zero, then the angle between velocity vector and the change of the velocity vector, delta v, will be approaching to 90 degrees. So this direction of the change of velocity, delta v, will be always perpendicular to the velocity vector. And in this very small displacement. In that case, the orientation of centripetal acceleration will be aligned along the position vector, which is actually the radius of the curvature with the center in the center of this circular trajectory. However, we cannot say anything so far about the exact orientation in terms, will it be oriented in the same direction as position vector, or it will be oriented in the opposite direction. So based on this phenomenological analysis, we cannot so far make any solid statement. However, we will come back to this point a bit later and will analytically show exact orientation of centripetal acceleration. So before we do that, we also need to mention, like introduce certain parameters which make it easy and convenient to analyze circular motion under some conditions. By the way, yeah, actually I forgot about that. If we don't have this condition that the linear velocity is constant, then we will have some acceleration. It's called tangential acceleration, which originates also from the change of the magnitude of the linear velocity vector. And this tangential acceleration will be always along the linear velocity vector, means perpendicular to the centripetal acceleration vector. So for instance, if we have some trajectory, then we have this particle here. This is velocity vector, which is not constant in amplitude anymore. Let's say we don't have uniform circular motion. Then in the same direction will be tangential acceleration vector. And here will be the so-called radial acceleration vector. Because if we have both they are usually called tangential and radial. Just in the names, it's already defined their orientation. And then the total acceleration vector will be defined as the sum of these two, originated from the change of the magnitude of velocity vector, tangential acceleration, and originated from the change of the position, like orientation, along moving along the circular trajectory, which is this radial acceleration. And then the total acceleration will be equal to square root a tangential is mean, here we consider absolute values, square plus a radial square. Okay, so this is just a short notice on the case when it is possible, of course, that velocity is not constant in magnitude, then definitely you need to deal with additional component of this total acceleration vector. Okay, but let's come back again to this uniform circular motion and introduce some like very important parameter as angular velocity, and also as also the period of we can write that linear velocity is equal to 2 pi times radius divided by some time interval t capital. So this in the numerator, as you may remember from geometry, it is just length of the circle, 2 pi times r. And here we have this period of this circular rotation. Means this is the time interval which is required for this particle to make like finish one total rotation about its axis along circular trajectory. So one total rotation, that is 2 pi radians, or this is equal to 360 degrees. Okay, so this is clear. Another important parameter is angular velocity, and that could be defined as this part. So this is actually omega, 2 pi over t over the period is given as omega, and omega is equal in its turn also to 2 pi times nu, where nu is the frequency, it's number of revolutions of this particle about its axis over along the circular trajectory per second, and nu is equal, as you may already see from all these combinations, 1 over t. So angular velocity is very important because we can express linear velocity as a function of radius of the circular motion with certain angular parameter like angular velocity. And it is very useful when we consider circular motion in polar system of coordinates, and exactly that we will do when we calculate the direction, like amplitude and direction of the centripetal acceleration. So we will operate in the angular system of coordinates, and we will operate with angular velocity. So linear velocity is equal to omega times t. And now for centripetal acceleration, we know that it's equal to linear velocity squared over over radius. So here I also made a mistake. Sorry, it's radius, not period. So we can substitute instead of v squared, like omega square times r square. This is divided by r. So we cancel out this square and this r in the denominator and end up with a simple expression for the centripetal acceleration, which is omega squared times r. So these are equations like this one for determination of centripetal acceleration in terms of linear acceleration, linear velocity, and in terms of angular velocity, you guys need to remember, and because that is basic of which is required for solving approximately all problems which are related with this topic of circular motion. Okay, now when all necessary parameters are introduced and defined, we can proceed to the analytical derivation of the expression for centripetal acceleration, not just amplitude, like magnitude, but also centripetal acceleration vector, which will tell us the exact orientation. So let us consider circular motion. First, we have some system of coordinates, x, y. Then we have our circular trajectory. There's some radius, which defines position of the particle which moves around this circular trajectory. Here, so we can put r vector. Here is linear velocity vector, v vector. Here is some angle theta, which is which defines the position of radius vector. And now what we need to do, we need to go from this polar, like setting the position of this point in the polar system of coordinates with radius vector and angle theta to this perpendicular system of coordinates x and y. So we want to find the projection of this radius vector on axis x and y. So this will be rx, this will be ry. So we already shortly discussed this, but you can already see from this triangular with angle theta, it's right angle triangular, so we can easily define this projection. So rx is equal to r times cosinus theta. And so here we take absolute value of radius. R y is equal to r sinus theta. So we know now these projections. We also, let's write here, define that this is uniform. This is important. Uniform circular motion. So absolute value of velocity vector is constant. Now let us define the radius vector in terms of its components, in terms of the projections, its projection on axis x and y. So we split this vector in two, that what we did previously, it's convenient, and we can write the following part. Radius vector is equal to Rx times I unit vector plus Ry times J unit vector. So let us substitute expressions for Rx and Ry. Will be R times I unit vector times cosinus theta plus J unit vector times sinus theta. Now we defined this radius vector or position vector. I call it radius vector here because it doesn't change in magnitude, but in general, you can call it also position vector. We define with this equation in a vector form exact position of this particle at a given moment of time. We don't have time here in this equation. And what is important for us, since we want to derive expressions for velocity, like our goal is to derive finally expression for the centripetal acceleration, and that is technically second derivative of the radius vector over time. If we want to take second derivative of radius vector, we need to present it, introduce it in the form which is a function of time. However, so far we don't have any time in this equation. So any ideas how we define this angle theta as a function of time?
Arctangents.
Can you repeat, please?
As arctangents.
Arctangents will give us the angle, but that's not our goal. We want to,
Like we can find the angular frequency.
okay.
Angular speed, I mean.
Yeah, angular velocity. Okay, that is correct. So we want to define this radius vector as a function of time. And for this purpose, from those parameters which we introduced on the previous slide, we know that theta angle, like position of this radius vector with respect to axis x, will be actually nothing else as angular velocity omega times t. So angular velocity means if we multiply it by, so it's radian per second. If we multiply per time, second and second will cancel each out. There will be only radians. So radians, that is angle theta. So this is how we can go from equation which defines just position in the current moment of time or some random moment of time, but just in one moment of time, to some time-dependent function by substituting theta with the expression omega times t. So let us do it. So that will be r. Again, r doesn't change. The magnitude of the radius vector, this position vector, doesn't change. It is just radius of this circle. But what is changing? Changing only theta. And that will be I unit vector times cosinus omega times t plus j unit vector times sinus omega times t. Okay, so now we have what we need. We have the time dependence of the position vector. So it should be like this. We know that our linear velocity, the amplitude of our like magnitude of our linear velocity vector is constant. It's given here. Then we know also that magnitude of linear velocity is defined by angular velocity. From previous slide, we know that v is equal to omega times r. So if v is constant, r is constant by definition because it's just circle, then omega is also constant. So that is important. We need to define all time-dependent parameters because next step, we will need to take derivatives. So why do we need to take derivatives? Because from previous discussions, we know that acceleration vector is equal to first derivative of velocity vector over time, or it is equal to the second derivative of the position vector over time. We can skip this time dependence. It's obvious that it is time dependent function. And here we need vector. Okay, so what do we need now? We need to get expression, like analytically derived expression for this acceleration vector. And since this is uniform circular motion, then we have only one acceleration component, which is centripetal acceleration. In order to do that, we need to take second derivative of expression for the position vector. So let us do it on the next slide. So dr vector over dt. So we take first derivative and then we will take second derivative. So this will be equal to r. Here, I think it's good to remind you that derivative of cosinus x is equal to minus sinus x, and derivative of sinus x is equal to cosinus x. So these are from table of derivatives, very basic derivatives. You can look it up in this table, but remember them. So our derivative, we need to take derivative of cosinus omega t, and that will be minus sinus omega t. So it will be minus I unit vector, but it's not enough because our argument in the cosinus is also time dependent. It's omega times t, which is omega constant, but t is time. So we need to take derivative also from the argument of the cosinus and multiply it to the derivative of the cosinus. So it will be omega times sinus omega t. Also, next component which we need to take derivative is this term with sinus omega t. So it will be j unit vector. Will be again omega because we need to take derivative from the argument of sinus, which is omega t. And now we multiply it by cosinus omega t. Okay, this is the first derivative of position vector. Now we need second derivative. So d square r dt square. So also our constant goes here, will be minus, so we already take derivative from these terms. It will be minus I unit vector times omega square times already cosinus omega t. And here again we have minus, will be j unit vector omega square sinus omega t. Okay, and we remember that this actually will be our acceleration vector. So let us see what we can do here. Let us take out of parentheses omega square and this minus. So it will be minus r times omega square. And what we have in parentheses, it will be I. Let's put r here. R here. I unit vector times cosinus omega t plus, because minus is here, j unit vector times sinus omega t. Okay. Do you see some similarities with previous equations which we considered? If we take a look on our previous slide, this is how we define our radius vector, our position vector. R times I vector times cosinus omega t plus j vector times sinus omega t. So if we go here, what do we see? We see that this is nothing else as our position vector. Means that acceleration vector is equal to minus omega square times position vector. And here we have analytically derived equation for the centripetal acceleration. We know that centripetal acceleration is equal to omega square r. We introduce this, and this is v squared divided by r. But previously, we didn't know exactly where it is pointed. Is it pointed towards the center of the trajectory, in the opposite direction to position vector, or in the same direction as position vector from the center. However, here, with the help of this analytical derivation, we clearly see that the orientation of centripetal acceleration is in the opposite direction of position vector r, because here we have minus, means that it will be always directed, like pointed, towards the center of the trajectory. Okay, so we are out of time, and this is everything what I wanted to tell you for our today's lecture. Any questions, guys?
No questions. No.
Just recall, we considered the circular motion, defined the magnitude of centripetal acceleration, but we were not from these similar triangulars of position and vectors and velocity vectors, but we were not sure about exact orientation. Then we introduced period and angular velocity, which is very helpful in while working with circular motion. And finally, we got the analytical expression for the position vector as a function of time by using angular velocity for uniform circular motion. And by taking second derivative of this position vector over time, we got the derived final equation for the centripetal acceleration vector, and have shown that our first derivation of the magnitude was correct. But in addition, we also know that for sure, the exact orientation of centripetal acceleration, which is pointed towards the center of the curvature, circular curvature, and it means that it's always in the opposite direction to the radius vector or position vector for this body. Okay, these are main points to take home, and I wish you relax during your long weekends. On Monday, we will not have our meeting since it's day off. So hope to see you already on our discussion on Wednesday. Take care.
Thank you.
And have a good day.
Bye.
Bye-bye.
Thank you.
Thank you,
Goodbye.
Professor. Have a
Thank you.
good weekend.
Goodbye.
Thank you.
Thank you. Goodbye.
Bye.